Performers. Where did I put the paper? Yep. Okay. We introduced performance transformer architectures which can estimate regular softmax full rank attention transformers with provable accuracy, but using only linear as opposed to quadratic space and time complexity, without relying on any priors such as sparsity or low rankedness. To approximate softmax attention kernels, performers use a novel fast attention via positive orthogonal random feature approach, favor plus, which may be of independent interest for scalable kernel methods. Favor plus can also be used to efficiently model kernelizable attention mechanisms beyond softmax. This representational power is crucial to accurately compare softmax with other kernels for the first time on large-scale tasks, beyond the reach of the regular transformers, and investigate optimal attention kernels. Performers are linear architectures fully computable with regular transformers and with strong theoretical guarantees, unbiased or nearly unbiased estimation of the attention matrix, uniform convergence, and low estimation variance. We tested performance on a rich set of tasks stretching from pixel prediction through text models to protein sequence modeling. We demonstrate competitive results with other examined efficient, sparse, and dense attention methods, showcasing effectiveness of the novel attention learning paradigm leveraged by performers. Okay, so this is version 1, September 2020. Let's see if it's the latest. Yeah, still the latest. Okay. Transformers are powerful neural network architectures that have become the state of the art in several areas of machine learning, including natural language processing, neural machine translation, document generation summarization, time series prediction, generative modeling, image generation, music generation, and bioinformatics. Transformers rely on a trainable attention mechanism that identifies complex dependencies between the elements of each input sequence. Unfortunately, the regular transformer scales quadratically with the number of tokens L in the input sequence, which is prohibitively expensive for large L, and precludes its usage in settings with limited computational resources, even for moderate values of L. Several solutions have been proposed to address this issue. Most approaches restrict the attention mechanism to attend to local neighborhoods or incorporate structural priors on attention, such as sparsity, pooling-based compression, clustering, binning, convolution techniques, which applies k-means clustering, to learn dynamic sparse attentions, or where locality sensitive hashing is used to group together tokens of similar embedding, sliding windows, or truncated targeting. There's also a long line of research of using dense attention matrices but defined by low rank kernels substituting softmax. Those methods critically rely on kernels admitting explicit representations as dot product of finite positive feature vectors. The approaches above do not aim to approximate regular attention, but rather propose simpler and more tractable attention mechanisms, often by incorporating additional constraints, identical query and key sets, as in or by trading regular sparse attention using more layers. Trading regular sparse attention using more layers. Unfortunately, there is lack of rigorous guarantees for the representation power produced by such methods, and sometimes the validity of sparsity patterns can only be verified empirically through trial and error by constructing special GPU operations, either writing C++ coded kernels or using TVMs or other techniques which aim to reduce transformers' space complexity, including reversible residual layers. Other techniques which aim to reduce transformer space complexity include reversible residual layers, allowing one-time activation, storage, and training, and shared attention weights. These constraints may impede attention to long sequence problems where approximation of attention mechanism are not sufficient, or approximations of the attention mechanism are not sufficient. Approximations based on truncated backpropagation are also unable to capture long-distance correlation since the gradients are only propagated inside a localized window. Other methods propose biased estimation of the regular attention, but only the non-causal setting of the large mean-square error. In response, we introduced the first transformer architectures performance capable of provably accurate and practical estimation of regular softmax full-rank attention, but only of linear space and time complexity and not relying on any priors such as sparsity or low rankness. Performance used the fast attention via positive orthogonal random features mechanism, leveraging new methods for approximating softmax and Gaussian kernels, which we propose. We believe those methods are of independent interest, contributing to the theory of scalable kernel methods. Consequently, performers are the first linear architecture fully compatible via small amounts of fine-tuning with regular transformers, providing strong theoretical guarantees, unbiased or nearly unbiased estimation of the attention matrix, uniform convergence, and low variance of the approximation. Favor Plus can also be applied to efficiently model other kernelizable attention mechanisms beyond softmax. This representational power is crucial to accurately compare softmax with other kernels for the first time on large-scale tasks that are beyond the reach of regular transformers, and find for them optimal attention kernels. Favor Plus can also be applied beyond the transformer scope as a more scalable replacement for regular attention, which itself has a wide variety of issues in computer vision, reinforcement learning, training with softmax cross entropy, and even combinatorial optimizations. We test performance on a rich set of tasks ranging from pixel prediction through text models to protein sequence modeling. We demonstrate competitive results with other examined efficient sparse and dense attention methods, showcasing the effectiveness of the novel attention learning paradigm leveraged by performers. We emphasize that in principle, favor plus can be combined with other techniques such as reversible layers or cluster-based attention. Okay. Favor plus mechanism and positive orthogonal random features. Below, we describe in detail favor plus mechanism, the backbone of performance architecture. We introduce a new method for estimating softmax and Gaussian kernels with positive orthogonal random features, which favor plus leverages for the robust, unbiased estimation of regular softmax attention, and show how favor plus can be applied for other attention kernels. Preliminaries, regular attention mechanism. Let L be the size of input sequence of tokens. The regular dot product attention is a mapping which accepts matrices Q, K, and V, which are size of L by D. Only Q and K have to be the same dimension. V doesn't have to. As input, where D is the hidden dimension of the latent representation. Matrices Q, K, and V are intermediate representations of the input, and their rows can be interpreted as queries, keys, and values of the continuous dictionary data structure, respectively. Bidirectional or non-directional. Okay, dot product attention has the following form, where A is an L by L, is the so-called attention matrix. So attention, bidirectional, is AV D is a normalization diagonal matrix. A is exponential. Yeah, so D is the so softmax is exponential of 1 over summation of exponential of all, right? So here, yeah, when you multiply a matrix of all, so A is the exponential of one particular row. So this is, I think, applied row wise. Sorry. So this is going to be L by L. Yeah. Divided by slash D. Yeah, just to make it numerically stable. So this is L by L, and exponential. This is for each element. When you multiply, each row will be summed. Yeah. So the output is one vector here, where each element in the vector is the sum of the entire row of A. So this is basically matrix A is measuring, this is K. Matrix A is measuring the response, how well query 1 or query 0 resonates with key 0, how well query 0 resonates with key 1, and so forth. But query 0 at the end will have to pick out certain, because these key will refer to certain values, right? So this is V0 up till V1. And this, for query 0, there is going to be a distribution of which values resonate. I should focus on more. This is the attention part, right? So this is going to be the sum of each row here is going to be 1, right? The the sum of this row of each row of this attention matrix is going to be 1. So you have to normalize by their sum. So their sum is just gotten here. Yeah. Here x is applied element-wise. 1L is the all ones vector of length L, and diag is the diagonal matrix with the input vector as the diagonal. Time and space complexity of computing 1 are L square D and L square plus LD respectively. Because A has to be stored explicitly. Hence, in principle, yeah, time is, yeah, space, yeah. Hence, in principle, dot product attention of type 1 is incompatible with end-to-end processing of long sequences. Bidirectional attention is applied in encoder self-attention and encoder-decoder attention in sequence-to-sequence architectures. Yeah, so here there is no causality. Each query is examining all the keys. So even in a causal sequence, you don't want like if you're here, you still haven't seen these, right? You don't want to consult with these, so you only consider what you've seen. So this is in the decoder, not in the encoder. In the decoder, these are decoder also elements. Like let's say you're translating a sentence from English to French, so you have already seen all the encoder elements, the English sentence, right? Sure, you can consult with any token here, but you cannot consult with tokens that you haven't seen in the decoder. You're generating this sequence, right? So you cannot consult with later on. So it's not bidirectional. So this is only one direction, which is backwards. You can only consult with what you've seen before. Yeah. Another important type of attention is unidirectional dot product attention, which is the form. Yeah, so you can only consult with queries that you've seen before. So you can't do this. Triangular lower, yeah. Attention. Query 0 here has not seen, forget about the encoder. If we're talking about the decoder, query 0 has only seen itself, cannot consult with these. So it can only see key 0. This guy can see keys of 0 and keys of 1, right? So it can do both. Only the last guy can consult with all. So only the last guy can consult with all. Yeah. It's the same, just you set this part to 0. Basically, there is no resonation between, triangular lower, basically, yeah. Where trill 0 returns the lower triangular part of the augmented matrix, including the diagonal. Yeah. As discussed is Vaswani. Unidirectional attention is used for autoregressive generative modeling as self-attention in generative transformers, as well as decoder part of the sequence-to-sequence transformers. We will show that attention matrix A can be approximated up to any precision in time, LD squared log D. For comparison, log D, wow. Like if you're using 512, for example, dimensions, where in fact, we actually in practice it's like 32 is used or something like that. 32 is 2 to the 5, right? So you're saying it's 5 times more time. Oh, it's not L squared D. Wait, what? Ah, this is L squared D. But usually the sequence is okay. Linear in the sequence, but quadratic in the dimension. So this is very prohibitive for large dimensions. We will show that attention matrix A can be approximated up to any precision in time. In time, big O of L D squared log D. For comparison, popular methods leveraging sparsity via locality sensitive hashing techniques have LD D squared log L time complexity. In the main body of the paper, we will describe favor plus for bidirectional attention. Completely analogous results can be obtained for the unidirectional variant via the mechanism of prefix sum. All details in Appendix B1. Okay. Generalized kernelizable attention. Favor plus works for the attention blocks using matrices A or L by L of the form Aij equals to a kernel over query I and key j, where query I key j standing for the ith and jth query and key row vector in q and k. Kernel kd to d to r positive is defined for the usually randomized mapping phi rd to r positive for some r greater than 0. Yeah, such that the kernel between two vectors is basically an estimator of the dot product after the transformation of these vectors. Expected dot product. We call phi u a random feature map for u in D, and q prime k prime in in RL times R. So this is after the transformation, with rows given as transformed QI and transformed KI, respectively. Equation, yeah. So leads directly to the efficient attention mechanism of the form. Okay, so basically, you assume that A is the kernelized matrix, which is transform the Q and transform the K transpose, and yeah, times V, yeah, and D is, of course, yeah, is A again with the rows sum. Yeah, here attention. So this is approximation attention bidirectional for the approximate attention, and bracket indicate the order of computations. Order of computation. Order of computation. You multiply Q, the transformed K in V. You multiply Q on both. You multiply. Okay, so that means we will not have, I'm guessing that we will not have either of these matrices explicit. Yeah, otherwise they would have factored it out in A. It is easy to see that such mechanism is characterized by space complexity LR plus LD plus L plus RD, and time complexity LRD, as opposed to L squared plus LD. Okay. Yeah. So this is LRD, RL, LD, and LR. Yeah. The above scheme constitutes the FA part. Yeah, okay. So this is kind of like, if you take it to the extreme, it's kind of like you're constructing the Gram matrix. Imagine X is a vector, right? But if you do vector transpose, one rank matrix, right? So let's say this is L and this is L. Yeah. So this dot is gonna give you L by L, right? Matrix. This dot product is gonna give you the L by L Gram matrix. And let's say you're multiplying it with a vector afterwards. Now you have, yeah, L cube, right? But it's easier that you could have multiplied this with this first, right? If you multiply this with this, this is an L, and then sorry. This with this would give you one dot, right? And then this, yeah. Each part will be multiplied with this. So it's 2L, isn't it? Am I mixing up my maths now? So if you multiply this with this, these are L, right? L elements, element wise, they are corresponding, and you sum them, yeah. And then, so this is scalar, right? It gives you one scalar, and you multiply with this. That's also applying the same scalar to all of them. So 2L. Whereas if you multiply these first, then you have to do this with this, this with this, this with this, this with this, and then this with this. There's going to be L by L matrix, and then each row, this with this, this with this, this with this, this with this, this with this. L times, right? And each time you have an L. So it's not L cube, sorry. It's this is 2L square. 2L square. So the square here is not needed if you have low rank, which is like which is like here. The rank is at most R, right? The rank is at most R. So yeah. I think this is L square plus L plus 2L. No, it's 2L square. I can't think. So we choose, so it's L rows, and each row when multiplied, that's an L multiplication operation. Yeah. Okay. The above scheme constitutes the FA part of the favor mechanism. FA is the fast attention. The remaining OR plus part is the orthogonal randomized matrices. Answers the following question. How expressive is the attention model defined in equation 3? How expressive is the attention model defined in equation 3? And in particular, can we use it in principle to approximate regular softmax attention? 2. How do we implement it robustly in practice? And in particular, can we choose R much less than L, much smaller than L, for L much larger than D to obtain desired space and time complexity gains? We answer these questions in the next sections. How to and how not to approximate softmax kernel for attention. It turns out that by taking phi of the following form for functions f1 to fl, f small l, r to r, function g, rd to r, and deterministic vectors, omega I to omega. What? And deterministic. Is this 4? I think it's 4. Omega 1 to m are IRD sampled for some distribution over RD. Okay, what the hell is H now? Okay, H over square root of M F1 omega 1 X F1 omega 1 omega mx. Okay. So these how they construct phi out of x. So it's not random. These are not random vectors. Where's G? What is G? I think this is H, not G, right? We can model most kernels used in practice. Furthermore, okay, citation needed, please. What? Furthermore, in most cases, D is isotropic with PDF function constant on a sphere, usually Gaussian. For example, by taking H equals to 1, L equals to 1. L equals to 1 means one function, one of those. And H equals to 1. And D is the multivariate isotropic. We obtain estimator of the so-called PNG kernel. F1 is sine, corresponds to the angular kernel. Configuration, H of x is 1, L is 2, F1 is sine, F2 is cosine. Corresponds to the shift invariant kernel. In particular, again, that Gaussian D leads to Gaussian kernel. K Gauss, Rahimi. Okay, the softmax kernel, which defines the regular attention matrix A, is given as the exponential of the dot product. In the above, without loss of generality, we omit the denormalization since we can equivalently renormalize input kernels, input keys, and queries. Okay. Since SM what is this? Why is it half? Oh. So Gauss, K Gauss equals x minus y squared, right? Which is x squared minus plus y squared minus 2x, sorry, minus 2x minus x transpose y, right? And the summation comes out. So K Gauss equals x squared x y squared and minus 2 sorry, over x 2 x transpose y, isn't it? Wait, let's repeat this. Assume K Gauss equals exp half x minus y squared. You end with K Gauss equals, I think K Gauss, there's minus here. I think there's minus here, yeah. X minus x squared over 2 x minus half and minus 2, these cancel each other, so end up x transpose y x minus y over 2. Take these on the other side, so you end up with x transpose y. You flip the indices, you flip the minus to positive. X squared over 2 K Gauss times x y squared over 2. Okay. Based on what we have said, we obtain a random feature map unbiased approximation of SM using the trigonometric functions with h of x equals exp x over 2. Yeah. L equal 2 and F1 is sine, F2 is cosine. We call it SM trigonometric. Yeah. So this is unbiased estimator of softmax. There is, however, a caveat there. The attention model from 1 constructs for each token a convex combination of value vectors with coefficients given as corresponding renormalized kernel scores. That is why kernels producing non-negative scores are used. Applying random feature maps with potentially negative dimension values, sine cosines, leads to unstable behaviors, especially when kernel scores are close to 0, which is the case for a lot of entries of A corresponding to not relevant tokens. Are approximated by estimators with large variance in such regions. Okay. This results in abnormal behaviors, e.g., negative diagonal values, renormalizes d minus 1, and consequently either completely prevents training or leads to suboptimal models. We demonstrate empirically that this is what happens for SM triag and provide detailed theoretical explanations showing that the variance of SM triag is large as approximated values tend to 0. Section 3. This is one of the main reasons why the robust random feature map mechanism for approximating regular softmax attention was never proposed. We propose a robust mechanism in this paper. Furthermore, The variance of our new unbiased positive random feature map estimator tends to 0 as approximated values tend to 0. Positive random feature maps, PRFs, for Softmax. For x, y, and RD, z is the sum of them. We have SM equals to the expected value, where omega is sampled from a multivariate Gaussian of dimensions d, exponential of omega transpose x minus x cubed minus x over 2 times exp omega transpose y minus y over 2 is equal to capital lambda expected as omega sampled from multivariate Gaussian of cosh of omega transpose z, where lambda is exponent of the norm minus the norms over 2, and cosh is hyperbolic cosine. Consequently, Softmax kernel admits a positive random feature map unbiased approximation with h being x, yeah, f1 being exp and d, okay, or h okay, f1 being exp and fu being minus exp, yeah, x minus u, and the same variance reduction we call related estimators. SM and S hyperbolic. Oh, okay. Be right back.